So I will talk about, as I just spoke about, network-based models for functional neuroimaging data, and I will focus upon fMRI data, but it's not necessarily limited to that. Some of these methods are very much more general. Give a brief interview, and then I will go on some recent developments that we have pursued in our group. So, I'll scroll forward for some reason. It worked before. Oh, yeah, now it works. You have magic fingers. Okay, so this slide summarizes what it's all about in terms of network-based modeling of neuroimaging data. So let's start with structural networks, which you can then study, for instance, by using diffusion-weighted MRI. You can track the white matter fibers using special sequences on MRI scanner, and the logic is here if region A and region B are somehow connected with axons, the white matter fibers. There is a physical connection between them, and then you can, of course, parcellate the whole brain from your diffusion data and study network properties of structural connectivity data. And you can, example properties here are either fully connected, all regions are connected to each other, and random networks should be over here. And then something in between is called small networks, small world networks, which you might have heard of, that you just change randomly a few nodes from being fully connected to random connected, and you get a very short medium path length. So many networks in nature have this small network capacity. So it's related to this that you are six nodes away from the actor Kevin Bacon that you might have heard of, the 6 handshake procedure. So you can do a lot of things with structural MRI and look at structural connectivity in the brain using network-based models. Then we can go on to functional networks, and you can use fMRI or MAG or EEG or intra EEG electrodes doing open surgery, for instance. And we say that each of 2 different regions, blue and red, they are connected if there is a correlation of activity that we measure over time. So it could either be quite weak, correlation coefficient 0.1, or stronger. So the strength of connectivity is determined by the degree of correlation. And then again, we can isolate the whole brain, model it as a network. Each brain region is a node in this network, and there is an edge between them if they are correlated over time from fMRI data, for instance. And the wider edges here signifies a stronger correlation. Then you can impose different tasks when people are in the scanner, and you can deduce then different properties that are related to, okay, in this case, for this specific task, the network, the blue network seems to be more within network connected than the red one, and vice versa for the other task, and you can draw conclusions from that. The third step is to look at what we call dynamic networks, so fluctuating brain activity. And there we, at each time point, so we have time series that we have extracted from the parcellation of the fMRI data. So each time point represents a parcel or a node in the brain matter, and a connection is present based on correlating activity through time. So we are interested in what is the degree of connectivity at this time versus that time, and so on. And then in this schematic here, we have 3 different brain regions, A, B, and C. And we can look at, it doesn't work for a wide screen, for instance, anyway. We can deduce when there is activity over time. It changes over time. So here is just a static picture over time, over the whole experiment that you have in the scanner. Here you can look at activity that changes over time. For instance, if there is oscillatory activity There are certain time intervals where you have a recurring pattern of activity. Or it could be bursty, which some people have speculated that you have a number of burst activity, correlation, connectivities, and then you have a longer period of absence of connectivity, and then it repeats itself like this. Okay, so that's a schematic picture that shows the kind of overview of network-based modeling of fMRI connectivity data. So one thing I would like to stress, we talk a lot about connectivity when we do fMRI and so on, and we measure the bold signal that you might know is the signal contrast that we can reduce, or we can say something about brain activity. It's actually a hemovascular response, but it has been shown to be indirectly correlated to electrical activity. What we really measure is correlation, not connectivity. So it's not good to have that in the back of your mind, that we talk about connectivity and we show different kinds of connectivity patterns. We are talking about correlations rather. And causality is out of the question, at least for fMRI, in my opinion. So what people then do is that they put people in the scanner, they scan them for some time, they do resting state, or they do tasks and so on, and then you parcellate your data. And there is a lot of different parcellations out there. In this particular one, there are parcellating the cortex into 264 nodes. And then you extract time courses for each and every pair, for each and every region, and then you pair them and compute the correlation coefficients between all those 264 nodes. And then you end up with a summarizing data like this in a kind of adjacency matrix, where each have nodes and nodes, and the value here indicates the degree of connectivity. So you see already here, there is a block structure here, signifying that there might be some networks or nodes that are more strongly connected to each other than others. And then you can visualize that by using this ball and stick figure, showing that different colors belongs to different networks and the degree of connectivity. So this is just a sample of there is a plethora of network metrics coming from graph theory, basically, in mathematics that you can apply to network-based models of connectivity. I'm just highlighting a few here. So you have nodes and edges, which is an abstraction of this parcellation of the brain. And you can talk about high degree. Some nodes are connected to many other regions, low degree or fewer connections. And you have shortest path. So if you have communication, you want neurons here to communicate with that node over here. Which is the shortest path? It might have some relevance if you want to transmit neuronal information in the network. You have hubs, nodes that play a significant role in communicating, because if you are somewhere here and you want to transfer data to all the nodes here, you have to pass through this node here. So that's the reason why you say this might be a hub. Similar to Heathrow might be a big hub for air traffic transportation, while the airport is not a hub, perhaps. And then there's also a concept of trying to group together networks that seems to be strongly correlated with each other compared to other groups of brain areas. So you talk about modules or communities. And the goal here is to try to isolate neurons that are strongly connected within the community or the module, and they have more sparse connectivity between the different communities. And I will come back to this later because it's an important concept in terms of looking at dynamic functional connectivity. But there are many more metrics. This is just a sample. So, and these parcellation schemes, there are plenty of them available to use. This is an example which is quite popular, called a Schaefer-Yeo parcellation scheme. And you see they have used different techniques to parcellate the brain into different regions. And you can yourself use or choose which granularity you want to use. If you want to have 100 nodes, 200 nodes, 400 nodes, up to 1,000 nodes. But there is, of course, a lot of parameters that plays a role here. Signal to noise ratio, the smaller the nodes you have, or the parcels, the less signal you will have, but you also want anatomical specificity on the other hand, so it's always a back and forth. And some of you might recognize here that, and all these nodes are then attached to communities, and here you might see the default node network in yellow here. The visual cortex is another network. I will come back to that later. But this is the kind of tools people use when they want to analyze their fMRI data, and also to some extent MEG data in terms of subnetworks that are interacting in the brain. So, and if you want to do dynamic or time-varying functional connectivity based on fMRI data, how do you go about to do that? Well, the most simple approach would be to just use a sliding window approach. So you have your time series of fMRI signal from two different subnetworks, the red and the blue, and they vary over time. And you're interested in the degree of connectivity or the degree of communication between these two subnetworks. And that's depicted here. And you want to establish how that degree of connectivity changes over time. So then you can just segment out the data and you compute the correlation coefficients for different windows. And then you step the number of windows consecutively. And then you end up with a diagram that shows the functional connectivity metrics as a function of the sliding window. So you'd end up with less data point here than up here, of course. And then you can do the same. If you have people lying in the scanner, you're often interested in some kind of behavior or some kind of other measure of their state of mind. It could be the galvanic skin response, it could be heart rate variability and so on. Use the same procedure on that signal, end up with a downsample plot of this variable over time. And then you can just correlate or do a regression between the two to see if the fluctuation in connectivity over time between these two networks have anything to do with the changing or the variability of these behavioral variables over time. So this is one of the, yes?
Can I ask you a question?
Yeah, sure.
How do you decide the windows? So
that's up to you as a researcher, but there are guidelines. So typically, the smaller the window, the less able you will be able to estimate correctly the covariance matrix, right? So you want as many sample points as possible to get a good estimate of correlation or the covariance matrix. On the other hand, if you make them really long, you lose temporal resolution.
Yeah, and as
so it's a kind of trade-off. Sorry?
You have overlap also.
Yes, yes.
So you can do.
Yeah, so they're overlapping, so they will be very smooth. But it's up to you. I mean, there are some rules out there, but it's up to you as a researcher and what kind of questions you ask, what kind of temporal resolution you're interested in, so on, what to choose.
Have you only mentioned the Pearson correlation? Do you use other? Pearson correlation.
Yeah, you can use Spearman also if you are in rank measures and so on. I mean, very often you don't find this to be normally distributed. So Spearman correlation is a good alternative as well. And you can also use other measures of mutual information and all kinds of parameter or methods to establish how the variance is related to each other. This is just a simple example. So is this all well and good for network neuroscience in terms of how we look at functional neuroimaging data? Well, it's not. There's of course problems with this. And one of the most fundamental ones, I think, is this concepts of redundancy and degeneracy when you apply a network model to your imaging data. So redundancy basically means that the same function is performed by identical nodes and edges. So if you have a specific function, it could be carried out by this particular set or that set or that set. There is no way to tell which one. Degeneracy means that structurally different nodes' edges may perform different functions. And a good example of this is the researcher Eve Marder at Brandeis University. She has studied the stomatogastric neurons in the American lobster, 40 neurons that regulates the gestation and the digestion and so on. And she found that a lot of different neuromodulators are introducing exactly this problem. The same network can actually do this exactly the same function. Different networks do different functions depending on the presence of different neurotransmitters and so on. So it's just to keep a warning that this is not simple. There are some limitations. So just to sum up, problems and challenges with fMRI-based human-brain connectome research. It's dependent on scale, of course. We can do this on neural circuits. We use electrophysiology, and you can have individual neurons and apply the same set of tools. And we can have fMRI, where you isolate the brain into 200 or 400 regions. And those results are applicable only to that scale. And the problem is how to transcend different scales to get really good, interesting information or relevant information that is kind of valid for different scales. It's, to a large extent, descriptive, I would say, and it's quantitative to some extent, but it has a limited mechanistic explanatory power. And it's very difficult to investigate causality, at least with fMRI. There is no consensus yet on naming these subnetworks, communities that I showed you before about default node networks and so on. But there is a lot of progress on this. And actually, there's a new paper now coming out in Network Neuroscience where they proposed a kind of agreement on what we should call them. And then we have the redundancy, degeneracy problem. The remaining of my talk, I would like to talk about brain states in network models of neuroimaging data. And I will sit down because my back hurts after some time when I'm standing up. I hope that's okay. So you hear brain states. You hear that all the time. I mean, a deceased brain, the healthy brain is a different state. You hear about sleep, different states. So it's a very common, I would say almost like a placeholder for different kinds of attributes we would like to have on the brain. So we like to think of things in discrete states. The brain are in different states. The brain is in a certain state when you do working memory. It's a different state when you do an emotion task or rest, etc., etc. And there is nothing wrong with that. I mean, it's well used, but I would like to, in this talk, to kind of give a kind of, it's kind of complicated because this shows you that states can arise on many different time scales. So on the top here, you have accuracy for an attention task, color emotion, that is in a millisecond range. I can say different states. And you can have attention that fluctuates up and down, and you have a network, one network configuration here to the right for high attention networks. And you have a different configuration in terms of brain networks for the low attention state. And that occurs perhaps in seconds or minutes. And then on top of that, you can have even slower processes that might be regarded as different brain states. You can say, let's say, hunger that has over minutes and hours that also might introduce different brain states. In this case, it was you see here as an example of a network analysis of caffeinated and not caffeinated state of mind. And then you, of course, on that you have mood changes. And this is example from the bipolar affective disorder, that you have mood changes over time, and that could take days or weeks or months. And you can talk about states for that as well. So it's the concept of states is kind of complicated, at least. And in terms of in fMRI, there has been a lot of emphasis when it comes to brain states to look at brain integration and segregation. That is related to this community concept that I talked about before, that you're looking for communities of brain regions that are closely knit together. They are integrated, and some others are segregated from each other. And this has been proposed that this dichotomy between integration and segregation is a key principle in brain function. And this is just two papers that have emphasized the relation of brain states to be able to determine brain states over time to different states of integration and segregation between these networks that you measure with fMRI, for instance. So you see there is a discrete number of states. In this case, it's 7, and it changes over time. And this was concluded by this sliding window approach I talked to you before, and then basically doing a key mean clustering into different states. And you see there is one state here. We have a transition matrix that shows you the probability of changing from one state to the next. And there is one state which has a high probability of staying in the same state. And here is also another paper showing that the brain toggles between being segregated and being integrated over time, back and forth, back and forth. And you can use a more different approach to this. You say, well, it's not that discrete. I mean, going from one state to the next, it's more like a probability. So you can use hidden marker models, and you know implicitly in hidden marker models you have states that just depend on the previous data. So this is one example of that kind of work. So over time in the scanner, fMRI scanner, you have a certain probability that state 4 is active, for instance. So here it's 0.5. And different states correspond to different connectivity patterns in the brain. So different connectivity patterns correspond to different states. And then you can somehow also come up with a graph showing that the brain cycles between different states in this manner. So if you are in a certain state, it's more probable that you end up in another state than the remaining states, so to speak. So this is how people have thought about brain states in the human brain using functional neuroimaging. So, and Marika, who's sitting over here, she came up with an idea, he's a postdoc in my group, that we should perhaps see if we can somehow investigate the possibility that network integration and segregation occurs simultaneously and independently in brain, rather than having just discrete states. So, and we also thought that using static over time network configuration is not the best option to address this problem. So we don't want the same. So we want the networks that we are working with should change their spatial topology over time, not only their functional degree of connectivity, because that seems like a more realistic one. Why should the topology be the same over time? And the key idea from Marika was also that we wish to capture both sustained integrated processes and more fleeting configurations of coactive brain areas. So both networks that live for a long time in terms of being integrated, and also networks that are more short-lived. And we should be able to capture both. And for that, we need an estimation of network connectivity at a time point by time point resolution. So we do functional connectivity, dynamic functional connectivity. And we said that the network we should work with, or the subnetworks, should be flexible, both in terms of spatial topology, as I said before, and also duration in time. So Marika set to work on this, and this is actually built on 4 steps. First, we do empirical mode decomposition and computation of intrinsic mode functions. I will not go into detail, but you can think of this as a bandpass filtering. We know that the Bose signal fluctuations reside below 0.1 hertz, at least the spontaneous ones. So this is just a bandpass filtering. Then we compute the instantaneous phase. So instead of just having a real value, we have a complex value with a phase and an amplitude. So be able to detect phase differences between different regions. We want to establish community membership. That was what I was referring to before, that we want to determine which regions are very close in phase to each other. Small phase differences means that they probably belong to the same community, that they are closely knit together because they are synchronized over time, right? And then from that on, and all these 3 points are well known in literature. This is something that has been done before. The new thing is how to build from the ground up, build network units we call them subnetworks and subnetwork components, at different levels of spatial granularity to be able to catch both fleeting connectivity patterns and sustained connectivity patterns. So to do this, or to explain this very in a kind of intuitive way, we have this toy example. So we have 60 parcels, 60 brain regions. So this is just a toy data example. You have sinusoidal, all the parcels in the subset 1, 10 parcels, they are fluctuating synchronously. And the same goes for the second and the third one, different numbers. And it's just sinusoidal waves that I put in with some added noise, uniform noise. And look also here, just to make things more interesting, I have changed the phase for a particular part of subset 3. So in this part here, they are synchronized with the nodes in subset 1. They change their allegiance, so to speak. They, instead of being tied together with the remaining nodes in subset 3, they are aligned with the nodes in subset 1. And then they release that again. So it's like to simulate this kind of that different networks hook onto each other. They connect and they integrate, and then they segregate again. So just to show the principle. And here is how the data looks like after the spatial filtering. We have the phase data that we will work with. You see it over here. And you see here that I'll show you better in the next slide. So you see here, this is the time course from the ones I've chosen over here. So you have phases over time. And you can see that the phase, sorry, oops, oh, something happened. Ah, sorry about that. Around time point 100, when we are here, you see that they start to align. The nodes up here start to align with the nodes down here. And then it starts to divert again. And then we compute the instantaneous phase at each time point. So we get a matrix. We have parcels on the X and Y axis. And the color here signifies the degree of phase coherence. We just take the cosine of the difference of phases between different brain regions. And cosine of if they are closely in phase, the phase is approaching 0. Cosine of 0 is, as you know, 1. So it goes from 1 to -1. -1 is they're completely out of phase with each other. And you see, okay, you see the nodes in region or subset 1 are closely connected or closely in space. Sorry, closely in phase. And also the same is true for the other 3 clusters or subsets. What's interesting is what happens at time point 100 when we start to go in this region here. Then all of a sudden you see that the nodes in part subset 1 also shows some allegiance to the nodes in subset 3. Is this clear? So, and then we have another key idea in Marika's work is that we want to establish communities in the networks, that dense groups of nodes which are tightly coupled to each other via a small phase difference are inside the group and loosely connected to the rest. We want to find those communities. And community detection is in general an ill-defined problem, so there is no universal definition, but there are many different methods that kind of iteratively try to come up with an optimal solution. Here we use the Levan community. There are others where you basically try to maximize the value Q, so you end up with the best possible community division of nodes into different communities that have strong, within communities, strong connectivity and weak connectivities between them. So, and then the key idea is to estimate how do we quantify integration across time from phase synchronization and community membership data. So the key idea here is to estimate differences in network integration or community membership, if they belong in the same community or if they belong in different communities in a whole experiment time. So we don't just look at integration at the time point by time point. We try to look at it over the whole experiment. So the key parameter here is QINT, which is a measure of temporal coupling strength between brain areas for the entire length of the fMRI experiment. So this is just to show you a very simple example. Let's say we have two brain parcels. We have done the community detection. So each brain parcel have been assigned to a community. In this case, 3 different communities. At each time point, we compare, are they in the same community? Okay, they get a 1. Are they in different communities over here? They get a 0 because they are not in the same community. And then we sum over all time points and divide by the number of time points. So for this particular example, we get a QINT of 0.6 because 60% of the time, they are in the same community. So this is the measure of strength over the whole experiment that these two regions are in the same community, i.e. they are closely integrated, the phase difference is small. So QINT ranges from 0, they are never in the same community throughout the whole experiment, never, and 1, they are closely knit together for all time points of the experiment. They're always in the same community. And then based on that QINT measure, we start to, from the bottom, just by pairing together nodes. Based on the QINT values, we group together those that have high QINT values. And then we gradually build up from 2, 4, 6, 8, etc. And we can do this indefinitely, but there is, of course, a limit of how large you want to make them. In this case, we settled for 8, but that's not a kind of a must. You can also go up higher. It depends on the parcellation, how many parcels you have, and so on. And from that, the next step is to merge together these that have great number of spatial overlap into subnetworks. So these can also be spatially overlapping. That's also a key ingredient here, that they can be partially overlapping, not identical, but they can be partially overlapping to be able to grasp this both sustained integration and fleeting correlations over time. Just to make it simple, let's start with our phase data. Up here, we compute the community using the Levan algorithm. And in this case, again, we have 3 communities, and you see for the 2 different lined up here, 2 different time courses of communities, and you see, and then we just combine them using the QINT value. So if they are in the same community, they keep that community value. If they are in different ones, then we set the community value set to 0. And the community value based on 0 or set to 0 means that they are not integrated, they are segregated. And here is the result of a Levan algorithm. You see here that you have 3 different communities, you have the 3 subsets, and you see up here when they are so to speak changing their allegiance to different communities, they are more aligned to subset 3 compared to subset 1. Oh, sorry, the other way around. So, and then we get a community vector for all these subnetwork components of size 2. And then we repeat this process for 4, 6, 8, and so on. And this is just to show you how the QINT values look like. If you have the example I showed you before, and you select the top pairs with the highest QINT values, compared to random, just randomly picking, you see that the QINT values are really high because you select the top ones up here. Here you randomly select, and they are out of phase with each other, so they would end up with a very low QINT value. Or some are by happenstance in the same subset, so they have high values here, but others are in different subsets, so they have low QINT values. And this is just an example of the larger subnetwork components. We have 8, and now you see we also incorporate parcels that are within this section here. You see again, they are not in the same community, and it means that during these time periods, the resulting 8 parcel subnetwork component will be disintegrated during these parts because it contains nodes that are in this region. So as you can see, it's very much data-driven, this method. Sometimes I would like to compare it to ICA, independent component analysis, blind source separation, but for networks instead. And this is just how it looks like for the toy data. You have a lot of subnetworks components of size 8 that spans the subset 2, 3, 1, but you also have some here that spans both 3 and 1. That kind of try to bridge together this phenomenon that they sometimes shift allegiance in terms of community. And for random, they're queuing the sphere. So the final step is then to combine all these subnetwork components into larger units, because we have a lot of them. We have over 2,500, just for the simple example. And we do that by ranking them, so average queuing values for SNCs across subjects. And we set how much of a spatial overlap do we tolerate. This is a manual parameter that you have to set. As a kind of example is that when you do an ICA analysis, you have to set the number of components you want to retain, typically. This is something that you have to try. It will be dependent, of course, upon the parcellation, the granularity of the parcellation. Here it is 5, so you rank them and then you merge all the SNCs together that have a large overlap. And then you take them out, and so you start over again until you have included all subnetwork components into a subnetwork. And a subnetwork is considered to be integrated at any given point in time if one of its constituent of the SNC that it's merged into it is integrated. So it's enough that one is integrated. So here from the toy example, this is all the subnetworks components. And if we apply these rules to compute subnetworks, we end up with 8. And here you see which parcels that are included in each subnetwork. We have 8 of them, and you can see it represents the 3 different subsets pretty well. But there are also ones that kind of bridges several subnetworks. And some subnetworks contain a lot of subnetwork components, and others very few. And they all have, at least the 6 ones have really high QA values, meaning that they are integrated for a lot of the time. And I mean, no wonder, because it's just sinusoidal waves most of the time, except here. But let's have a closer look at subnetwork number 5 here, which kind of encapsulates most of what's going on in this subset here, and see how that looks like. So again, the data. And here you have the community membership for all parcels that are included in subnetwork 5. Here you see subset 1, but also someone in this rogue parcels in subset 3, which were temporarily out of phase with the remaining parcels in subset 3. And all the SNCs, they are not identical, or might look like so, but they're not identical. You see it encapsulates all the SNCs subset 1, but also some of the parcels in subset 3 up here. So you can then compute community memberships for subnetworks. You see sometimes it's disintegrated, have a 0 value, and then it's integrated most of the time. And here, from this, we can reconstruct the phase of that, and the phase 0 means that it's not integrated at all, and it's fairly well represents what you see here. So let's go to some real data. That was the toy example, just to explain in so many words how this data-driven method works. So this is from the Human Connectome project data that you might have heard of. 100 subjects doing working memory and rest. And you have the phase data over there that you work with. And here you compute the instantaneous phase data for different time points. And you see it looks quite different from the toy example I showed you before. Here are the abbreviations for the different networks that you work with: visual, somatomotor, dorsal attention, ventral attention, limbic, frontoparietal network, default mode network, basal ganglia, and thalamus. And here we have all the subnetwork components, the smaller units, 8 parcels of each. We end up with a huge number, 36,000. And then we do the subnetwork, then we merge them together into subnetworks. And here we see that subnetworks we have in total 375, and they range from qint values up to 70%, meaning that the most integrated networks doing the working memory task is integrated for 70% of the time, while many are more fleeting. They are integrated for a very small period of time, which kind of resonates with what I talked to in the beginning. You want to capture both. And some of the most integrated ones, they also contains a lot of subnetwork components. They are very similar. They just differ by a parcel or two. And this is how it looks like for the working memory. This is a two-back working memory task, by the way. Do everybody knows what two-back working memory task is? Everybody? So it's basically two-back. You get a list of words or figures, and you have a queue, and then you have to compare that queue to either what you saw 2 times before. So then you have to say yes or no if it matches. So then, yeah, so you can change the difficulties by doing 3-back and 4-back and so on, which is impossible almost. So here is the working memory, the most integrated network, about 70% of the time. And you see it's sometimes disintegrated, 2-back, 0-back, rest, and so on. And it comes to for all the classical working memory tasks regions. You have the dorsolateral prefrontal cortex, you have visual cortex, posterior parietal cortex, you have the thalamus, etc. So that's one of them. Another one is over here, which shows the motor cortex combined with the visual cortex. It's not integrated only 44% of the time. And you get also more networks which are more fleeting. This is the posterior parietal cortex coupled with the frontal eye fields, 27% of the time. And you have, here you might recognize the default mode network, which is not very much connected at all during the working memory task. And here's just a small movie showing that I talked about how these networks integrate and segregate over time. So how about the spatial change over time, the topology, how many regions are involved, because these are flexible. So this is just a movie showing you, now it's the 2-back task the subject is doing, and you see that this network builds up, starts in one region and then gradually fills the whole working memory task. And what you see, the color is the phase of the signal. So it's basically a wave that starts at some point and then it goes back up and back and forth again for the working memory task. So I speed it up a little bit. In the interest of time, I go on. If you do rest, spontaneous rest, you ask people not to do anything else in the camera or not do anything at all. You basically get the canonical resting state networks. You have default mode network, visual, default mode, attention networks, and the somewhat motor network. And if you compare the mean phase, you get 0 because everybody is not constrained by the experiment. Nobody tells you to do what, when. So all have their own phases, so to speak. So when you average over 100 subjects, you get averages out. So this is doing rest. And I think you recognize this is the default mode network that kind of handles back and forth. Changes both in time and space. This is just a diagram showing you this red is for surrogate data. It was just phase randomized using the Fourier method to just compare that we are not just looking at noise. And you see the instances of integration versus the duration of integration. You see some networks, each dot here is a subnetwork, and some networks are integrated for quite some time, and others are integrated, or the majority of them are integrated just for a very short period of time. And you also have, if you look at the amplitude of the different subnetworks, you see this kind of quasi-periodic pattern of increase and decrease of amplitudes, which has been also been noted by other research groups, that you have this periodicity of fluctuations in the amplitude of the waves. But the reason why you don't see it during rest is the same reason I said before, because it's not constrained by experiments. So they have, but you see the same pattern at the individual level for rest. So just a brief summary then. I have presented a data-driven method to extract sustained as well as temporally fleeting behavior of network integration. So I think we have shown that segregation and integration occur simultaneously, which kind of complicates the picture of the brain being an individual specific states. So it's just an alternative view on how you can look at the data. And you have this quasi-periodic behavior of subnetworks that implies the kind of repetitive process which consists of gradual buildup and dismantlement of subnetworks, which might be a core function of core feature of brain function. And during task performance, like in the working task I showed you, global changes in synchronization between networks arises up and down, which are tied to the underlying temporal design of the experiment. And limitations, of course, all methods have limitations. It depends on the granularity of the spatial oscillation. It depends on some user-defined parameters, namely one of them is a spatial overlap it would allow. The temporal frequency of the signal that you look at. Remember I told you about narrow passband filtering. If you look at different frequency ranges, it looks differently. And if you're interested in the details, you can read Marika's paper and also a follow-up paper down there. So then I'm ready to take questions.
Okay, so are there any questions, either here or virtual?
Arvin, you can open your mic.
Thanks so much, Peter. Regarding this working memory task, I was just wondering, you showed that quite a large fraction of the brain is activated in relatively simple tasks, if you think about it.
Yeah.
By contrast, if you look into these brain areas and you go there with electrodes, very few neurons seem to be reacting.
Yeah.
So how do you reconcile this microscopic representation of working memory as opposed to the macroscopic?
That's a good question. It kind of relates to what I mentioned before about the problem of scale.
Yeah.
Depends on what the bold signal requires the simultaneous activation or excitation or action potentials of hundreds of thousands of neurons simultaneously to be able to detect the signal. So, as you said, it might not be straightforward compatible, but on the other hand, when you do electrophysiology, you can only sample a small part of the brain region. You don't know what's going on in the rest, right? So you have a very specific idea or evidence of what's happening in that particular area that you're probing. But on the other hand, you don't know what's going on in the rest of the brain. So there has been a number of papers now showing that if you have enough signal to noise, if you scan people, it's called dense sampling method for fMRI, you can deduce, I think, that a lot of the brain is actually activated one way or the other. Not always positive activation, but also negative activations for a relatively simple task as a working memory task. But I think working memory is not that simple. There are several components. You have a maintenance component, and you have an update component, and so on. So yeah, but I don't have a straight answer to why we don't see a direct correspondence between classical electrophysiology and fMRI, but the gap in scale is huge.
Can I ask one more question?
Sure.
It's a more general question about networks. So I guess you have seen this paper from Pang and Fornito, I guess.
Yeah, about the geometry.
Right. So how do we take this? I mean, so they are saying that long-range connections are not relevant. All you need to worry about is the specific geometry.
They is more like a parsimonious approach, saying that waves can explain everything in the brain if you take into account the specific geometry that and they say that traditionally you would start with a structural connectivity, and you have a structural connectome and say which regions are linked to what, and then you base your generative model based on that. If you have a oscillator model or whatever you have, and you base that on a structural connectivity. What they are saying is, if I understand it correctly, that doesn't tell you the whole story. Their approach of looking at the geometry, and I think they computed a Laplacian operator for a number. We have a superposition of different waves, and I think the waves were, the ones which are longer than 40 millimeters were kind of playing a prominent role in that paper, if I remember correctly. So it's a very interesting paper, and we'll see if that really. I think one of the criticism I read from David van Essen about that paper was that if you do a very small stimulation, let's say a very brief visual activation, can you represent such a point-like activation pattern with that kind of wave framework? And I think that would be very interesting to see if they can do that with that kind of model. But
Yeah.
it's interesting that, I mean, I'm kind of surprised that the geometry played such a role.
Yeah, I mean, I'm kind of, my gut reaction was that there is something wrong with that paper. Because, I mean, how could it be that you ignore all these long-range connections, which are so crucial, right? You lose.
Yeah, it's like, okay, this is your spatial Fourier transforms.
Yeah, exactly.
What's the deal here? So I am struggling to get through all the model assumptions they make and how they compute the Laplacian. It's probably very computational intensive because they have this mesh. They approximate the cortex with a mesh. I think 33,000 vertices, and then they have to compute from that. But I didn't really understand how they get to the specific activation patterns that you got from the Human Connectome project, where you have memory, emotion, etc., etc. They could replicate that almost identical and even better. And I still haven't gone through the paper deep enough to really understand how they achieve that.
Thank you, Peter.
Thank you.
Other questions?
Maybe also a more general question. I'm curious about the fact that usually we use structural connectivity and functional connectivity, and structural connectivity is most of the time given by the diffusion number, which is from the white matter. What's your opinion on the effect of the connectivity within the gray matter?
I think structural connectivity, if you even do it high resolution with all the best diffusion gradients that are available, I think people have made comparisons. How much of the variance from functional connectivity and scanner can be explained by the structural connector? And I think the figure ranges between 50 and 60%. So it's not the whole story, because monosynaptic connections, of course, but polysynaptic connections you cannot get at from the structural connector.
You know, if there are some way to recover some of this connection between.
You mean the white matter?
There's a connection between cortical areas. Like.
Yeah, I mean the best, the golden standard, so to speak, is to do intracranial EEG or intracranial. I have a postdoc who's working in Stanford right now. They have patients with are untreatable with pharmacological treatment. So they do open surgery, and you can position grids, ECOGs over the brain, and you can. But it's still kind of an averaging procedure. But you can't get closer than that, and that's what kind of would be very interesting to see what they come out of that in terms of networks. But the analysis is very different compared to fMRI, that data, because timing is very sensitive.
I was thinking maybe using modeling we could, and trying to gain more, try to explain the functional connectivity from the structural connectivity, but adding nodes in the.
As I said before, I think there are limitations of the kind of information you will get from structural connectivity. Sure, you get the main fibers and so on, but I mean that's not. I mean, you want that to constrain your model, right? And that is not the case. That it kind of constrains, so everything which is outside that it's what's in the brain. It's not true, I think. It's certainly helpful in many situations, but it's not a kind of magic wand that you can use and say, this is because I've used this, everything I can, all structural connectivity is there in my model, and I will only use that, and then that's it. So I don't think it works that way.
Well, one quick question, maybe.
Okay.
So I was happy that you brought up the brain states, because many have mentioned brain states in previous talks today, and you really showed that the canonical brain states that we look at is one thing, but they transition very fast, and there are states within the states, even if you look at them closely.
Exactly.
So with the development of methodologies and computational power, where do you see we go from here when it comes to brain states?
Well, what I presented here, Marika's work, is a kind of alternative view on that we can measure or try to go simultaneous integration and segregation. But most of this brain state business is based on integration and segregation. Or if you don't have a very strong, if you have people under anesthesia, for instance, or so on, then you can say, well, this is definitely a brain state. But I think complementary views might be useful, that you have this kind of data-driven methods and try to see that there are perhaps things going on, which I think nobody really believes that the brain goes through very discrete. So now it's state 1, and then state 2, and then state 3. I think that's kind of a too simplified picture of how the brain does. And as you mentioned also, that you can have a hierarchy of different meta states, and this meta state can be composed of different smaller states and so on. But I mean, it has been the concept of states has been very prevalent in the literature, and it's easy to grasp and it's easy to discuss. But it's perhaps it would be interesting to see how far we can get in terms of data analysis and try to understand how useful is the concept of states in the brain. When we try to try to understand the relationship between cognition and brain connectivity that we are trying to do.
Okay, then